where your answer is really going to come from is evaluating the difference between kinetics and thermodynamics. Okay? And so what we're looking at in our first answer, where we said the bottom one was the more stable, is that we're evaluating the stability of the most reactive thing and saying, well, it's more substituted on the bottom, which then makes it lower in energy, which makes it the thermodynamic product, okay? Or at least thermodynamically favored. Okay? If we flip that on its head and say, well, but there's other things involved in this. There's also that intermediate. Well, that intermediate also contributes on how we get to the product. So we have to consider the intermediate. And when we go back and look at the intermediate, we have a negative charge on a tertiary position versus a negative charge on a secondary. The secondary is more likely to form, which then means the product that we would get from that should happen first. So we would get the kinetic product because it's happening faster. And there is this weird kind of spread between them. We saw that same spread when you looked at 152. There were two aspects in second semester Gen Chem. Okay? You had the kinetic part, how fast did the reaction occur, looking at mechanisms and all of that. And then you also had the thermodynamic part, looking at equilibrium constants. We don't care about how fast it occurs, I just care if it occurs. Okay? Those two things we can separate fairly cleanly away from each other and look at them in Gen Chem. In OChem, we kind of have to look at a blend of both and decide what's going to push us down one path versus the other. And a lot of that's going to come down to the raw energy diagrams and the actual energy values that's happening in each of those cases. Because we don't quantify, at least I don't quantify, our energy diagrams, we have to come up with some kind of hand-wavy approximations. And while we might say, well, that's really bad, our hand-wavy approximations work. Okay? So this is one of the reasons why organic chemistry tends to freak people out, is they go, well, but I had all these numbers that I relied on to allow me to solve and do all this. And well, all those numbers work. And we can find those for OChem. But the effort it takes to go through and do that is more effort than if we just look at it and say, it's not going to like to do that. Right? And so what we're trying to do is think about those conditions and how it's going to cause things to change. So what we would do is build an energy diagram to represent each of those. Okay? I've been attempting to color code red as our thermodynamic and blue as our kinetic. So I'll try and keep that running. In both cases, we have the same energy for our reactant. Okay? Our intermediates. Okay? We said the kinetic was lower in energy than our thermodynamic, so we'll show our thermodynamic, our kinetic underneath it. Both of them should be higher in energy than the reactant. Why? They're charged. I don't know why it took me so long to acknowledge that, but you're right. Okay. So our kinetic is lower in energy. If we go to our products, the highest energy system is now the pi bond. The pi bond is now lower in energy than our intermediates. So we could draw in our thermodynamic and our kinetic. Our kinetic would be higher in energy because the pi bond was less stable. If we went through and tried to draw everything out, oof, it's close enough to hitting that line. Okay. We would notice that our lines cross. Okay. That crossing is important because that's what differentiates our kinetic versus our thermodynamic and why we see this issue happening. Okay. If they stay matched evenly all the way through, okay, then we only have one product, really, okay, or one issue. Both the kinetic product and the thermodynamic product would be the same thing. In this case, because there's a cross, we get two different options. Okay? So when we look at this, we can try and evaluate with the simple conditions we've already done in the past. We can add energy. If I want a reaction to occur, I can add energy so that it clears the activation barrier. So let's add tons of energy. Okay? So under case study, let's just call it A, tons of energy. What happens? Well, I start with some reactant. With that energy, that reactant can now roll over the barriers between those wells. Okay, so we just pretend it's a ball on a hill. Okay, we give it enough energy it can roll. It will very likely roll over the lowest energy first. Why? It's easy.
It's lower in energy.
It's the lower hill. That's why. Right? Simple. It's lower in energy. It's easier to clear that hill than it is to clear the higher hill. That's it. Okay? If we're going to try and transverse the Rockies, we don't find the tallest peak and climb over the tallest peak to make it to the other side. Okay? When people are moving through Tibet and Mount Everest, does everybody climb Mount Everest to cross from, let's say, India into China? Because Tibet's in the middle. Okay, since no one knows, we'll just accept it that I'm right. Everybody doesn't go through Everest. Why not? There's an easier way. There's lower areas. So we'll go that lower pathway first. Okay? So it will roll over to make the kinetic product. Okay? So my reactant, my little reactant ball here, has now jumped to becoming the kinetic product. But when we run a reaction, do we look at it and go, oh, there's product, stop? No. We said, well, I think it's going to keep reacting, so I'm going to keep letting it react for a little bit. We have tons of energy. We have enough energy that what can happen? We can clear the reverse as well. That reaction is now reversible. Okay? That's what that tons of energy provides me. Which then means I'm no longer looking at my ball in the kinetic well. Okay? It's now back at the reactant well. It still has tons of energy. One of those times, it happens to roll all the way up, clear Everest, and down the other end. Okay? It now makes it into the thermodynamic well. What is the problem with being in the thermodynamic well? It can't roll back. There's now an even larger energy gap there that it can't overcome, which means I'm now stuck as a product. The instant I now fall into that thermodynamic well, game's over. Okay? It doesn't matter how much longer I wait, I'm now stuck. And I'm stuck in that irreversible spot. I cannot now reverse. Okay? So under circumstances of very high energy, we tend to see just the thermodynamic product and much less so of the kinetic. That's because the kinetic under that high energy condition is reversible. The thermodynamic is not. Okay? So we see a larger amount of the thermodynamic product. Okay? To add kind of a complexity to this, remember those are all equilibrium arrows. Our equilibrium is now bouncing back and forth between all of these individual states except for the thermodynamic. When we look at the thermodynamic, that last arrow is unidirectional, which then means the instant I remove this species, what happens to the equilibrium in that spot? It shifts to favor more of the intermediate. Well, now that intermediate can potentially form product, and it can't reform the intermediate. I've lost intermediate. Well, Le Chatelier then says, well, make more intermediate from the reactant. And so what we end up seeing is a vicious cycle. Vicious. We see a cycle here of not two reactions, but really one reaction, going from the kinetic product all the way around to the thermodynamic product. And in circumstances of very high energy, the thermodynamic is only one directional, which means I can only get the thermodynamic product. What happens if I drop the energy, though? So we move to new conditions, low energy. Most likely thing to happen will be what? Okay. We're still going to see the kinetic product form first. Absolutely. It is the lower energy that is going to happen. Okay. So my little ball can jump across to the kinetic well. But now that I'm in low energy conditions, what happens to the reverse reaction? Kind of accept shaking your head. By shaking your head, what are you saying? I can't clear that activation barrier. That reaction is now irreversible. Because it is irreversible, I don't expect a lot of the thermodynamic product because all of my product is now shuttled into the kinetic well and now it's stuck there. It can't get back. The thermodynamic product can still form, okay? Because we have billions of particles floating around. There is an opportunity to form some of the thermodynamic product, but most of it, based off of that energy difference, is going to be the kinetic product. Kind of makes sense? Okay. That's just changing the energy. So one of the things that I want to address here is our use of the term reversible. When we started this with high energy, what did we say the kinetic product was? This is where we could pause the video and go all the way back and check our notes. We said it was reversible, and yet what am I labeling it now? Irreversible. Why? The conditions have changed. Because the conditions have changed, that has now changed my interpretation of reversible and irreversible. Okay? So we have to be careful when we use those terms to make sure we're applying them correctly. Applying them to your kinetic and thermodynamic products is a very dicey situation. Okay? Because you're now applying them to things that can change. You should really be applying your reversible and irreversible to the conditions. Okay? At high energy, our kinetic product is reversible. At low energy, our kinetic product is irreversible. Does that make sense? So we're labeling the conditions based off of reversibility, not the species. Because the species can change their labeling very quickly. The conditions can't. Sorta? Okay. Before we even got into this, though, the previous slide looked at, I don't even remember what it was now. I think it was ethoxide. Anybody remember? Negative oxygen, negative hydrogen, negative nitrogen. We looked at those three things. Are those three things anything to do necessarily with our energy or our heat? Whoops, ignore that. Does oxygen say anything about temperature? No. Okay. Does hydrogen say anything about temperature? No. Temperatures like Celsius, Fahrenheit, Kelvin. Hydrogen is not a temperature. Okay. But those are different. What kind of species? Negative oxygen, negative nitrogen, negative hydrogen. All those species can act as what? What's that? They could act as nucleophiles. Am I running a nucleophile reaction? No. What kind of reaction am I running? Okay. We can either look at this one, or we could even look at this one. I'll accept both. Purple arrow, what are we doing? It's kind of tricky. We've changed the location of a hydrogen and the location of the pi bond. Okay, really all we did was change the location of the hydrogen and the electrons just kind of floated around accordingly. Okay, which means what kind of reaction do I do? What reaction just changes the location of hydrogen? An acid base. What can a negatively charged oxygen, nitrogen, or hydrogen do? Act as a base. Okay. Are all those bases equivalent in their functionality? No. Okay. And I think you just said what? No. Are you just saying that because I'm calling you out for it? Okay. Well, we're just going to work with the assumption that you said what. Okay, what do I mean by that? We take a look at those three reactions, negative oxygen, negative hydrogen, negative nitrogen, right? Okay. Do they all act the same? They all remove a hydrogen. Why are you saying they're different? What is different about those three reactions? What do you mean the reactivity? How can you tell that?
How stable they are on their own after they react.
So you're saying this is less stable than this?
No. The actual thing that's reacting. So like the hydrogen.
So you're saying this is between those two circled things sometimes?
Further down.
What are you saying?
The hydrogen and the oxygen.
Okay, we're evaluating those. How do you know those are different in reactivity?
Well, the oxygen's going to be more stable with a negative charge than the hydrogen.
Why
because
is
of size.
yes? Yeah, I'll accept that. Right. So we could evaluate those 5 rules: charge, size, electronegativity, resonance, all of that fun stuff, and evaluate those differences. Okay. We actually want to take a step further beyond this. Okay. We're actually adding an extra layer to it. What is that extra layer? There's another hint here that explains the difference in reactivity. That is actually already written into the slide. Should that first reaction progress forwards? No. Why not?
I just looked at the arrows.
Right? I like how you said that. I just looked at the arrows like I'm cheating. I didn't really mean to do it. It's just there. That's exactly what I want you to do. There's information there. Use it. That information is saying that that reaction does not favor products. That does not work as an acid-base reaction, but the other ones do. Okay? Of course, now I'll be irritating, and I'll say there's something else there that you should be using. It's where I thought Wyatt was going, but then I was wrong. We're comparing left to right, the most reactive species on each side of the equation. Negative carbon versus negative oxygen. Negative oxygen is a little bit more stable. We would predict that reaction to stay on the left. How about the next one? Negative carbon or negative hydrogen? Negative carbon. The reaction favors the products. Okay? So we have that information buried in there somewhere. Okay? So there is a difference between those. It has to do with the strength of the base. The strength of that base we can use to evaluate the directionality of the reaction. Okay? Whether the reaction might be reversible or not. Okay? Sorry? We go to the bottom one, same situation, trying to evaluate our differences there. We might expect the nitrogen to be a better place to hold the charge than the carbon. Is that what you're suggesting?
Yeah, why is it not?
It's not carbon holding the charge.
Okay.
What atom is it? It's the oxygen. Through resonance. Okay? Oxygen's better at holding that charge than the nitrogen. Okay? So we have directionalities on these. With the oxygen, that reaction is reversible. With the hydrogen and the nitrogen, it is irreversible.
So the resonance doesn't work in the top one.
Resonance is working in the top one. It's oxygen versus oxygen is your charge. There's a little bit of resonance, but how good is that resonance? You're making a negative carbon. That's not very good. Really, that resonance up there is darn close to being equal. If we look at the pKa's, it's barely a factor of 10. Okay? So those are very, very close in reactivity. Okay? So let's now scaffold this back out to our reaction. Let's just pick one for the sake of it. Yeah, we're just going to do it. Okay. When we drew this out, we drew it something like that, right? We went up in energy and we went down in energy. Okay. More than likely with that enolate, they're probably pretty close in energy to each other. In fact, I think it's actually the other direction. The carbonyl is slightly more stable than the enol form. Okay. So we would expect something a little bit like that. So they're pretty close. Okay. That's just evaluating the keto-enol tautomerization. What happens when we throw in the base? Okay. We have H minus going to O minus, right? Which is more stable? O minus. Is our energy diagram going to change? Yeah, how's it going to change? We'll even draw the reactant being the same energy. Is that red one reversible? No. If I use hydride as a base, I'm now running an irreversible reaction. Which product forms? The kinetic or the thermodynamic? Okay. So I got both, I got kinetic, and I got thermodynamic. This is awesome. Okay. There's our thermo. There's our kinetic, right, Cliff? Okay, that's too small, sorry. It's not much better, but it's close enough. Okay. Which product forms first? Kinetic. When? When does the kinetic product form first? Say that again? No. No. When does the kinetic product form? Always. The kinetic product always forms first. Period. No exception. Okay. If I'm running H minus as my base, what happens? I form the kinetic product, but remember this now doesn't accurately reflect. Because H minus says that that reaction should be massively exothermic. And really what I'm looking at is not that situation, but really at the situation like this. So now I'm using that really strong base. Yes, I do form that kinetic product. What happens to the reversibility now of that? I can't reverse it. So when I use that stupidly strong base, I get the kinetic product only because I'm now in an irreversible situation. The stupidly strong base prevents the reversible reaction. If I now use a weaker base, say with the O minus, what happens? Well, we're going to get those same two drawings, but their energies are now going to end up somewhere up here. Is that now a reversible gap? Yeah. So now with a little bit of energy, I can reverse that. So by changing the strength of the base, I can oscillate between either having the kinetic product or the thermodynamic. It's not just temperature, it is also base driven. I think that's really neat. What do you need to know? Hydride and nitrogen, when they're both negatively charged, are irreversible. Being irreversible, what product do we get? The kinetic. Oxygen as a negative charge is reversible, which gets us thermodynamic. At high energies, I am reversible, which gets me thermodynamic. At low energy, I am irreversible, which gets me kinetic. Right? Make sense? I would love to say that I have that written out on a nice little slide where we can all just look at it and be like, yippee, I haven't done that, sorry, and it's too many words for me to write down. So, rewatch the video if you want to take notes. That just happened about minute 22 to 24. Okay? So, where this all then comes back to is this god-awful, nasty-looking, massive slide. Okay? Starting with the very center branching out. You have the keto-enol tautomerization. If you run under base conditions, you get the enolate. If you run under acidic conditions, you get the enol. The enolate and the enol are your active nucleophile. Depending on what you then react that nucleophile with, you can branch out into tons of different situations. Okay? The upper left, okay, this was our chapter 10. That was the tail end of chapter 10. We were adding it to an electrophile, bromine, simple electrophile. Okay? Upper right, at least for that first part, we're adding that to a carbon electrophile. I'm going to draw that as a carbon. Okay? Again, simple substitution. Okay? Again, chapter 10 for that first step of it. Okay? What happens when we look at subsequent steps? What's happening due left? Now highlighted in kind of blue. Everybody see it? What happened there? That looks kind of weird, right? Maybe it'll help if I do this. Does that look a little more obvious yet? What happened? A bond was formed. A bond between what? I don't accept between ketones, you're right. We have a nucleophilic carbon attacking what? An electrophilic carbon. Where's that electrophilic carbon found?
Carbon is attached to the oxygen.
That middle carbon? Yes, exactly right. That carbonyl is electrophilic. And if I take a nucleophile and attack that carbonyl, I'm now doing a nucleophilic addition. Right? And you might say, well, isn't that kind of weird? Because we did additions before with alkenes, right? And what did alkenes act as? Nucleophiles. They were a source of electrons, which means whenever we reacted an alkene, we reacted it with an electrophile. We never reacted them with nucleophiles because that's negative to negative, and that's bad. We can't do that. But I'm saying a negative is now attacking the carbon of the pi bond. Because why is the carbon partially positive? Because of resonance with the oxygen. It's polarizing it. We are doing a nucleophilic addition. The only reason we can do that nucleophilic addition is because we have a polar pi bond. That polar pi bond is what sets off the cascade of reactions that we're seeing up here. Okay? All of them are virtually identical to each other, but instead of being a carbonyl from a ketone, it's a carbonyl from an ester, or a carbonyl from an aldehyde, or a carbonyl from a carboxylic acid. And because of that, it gets named by somebody else. You get Claisen, you get Dieckmann, okay? You get aldols. Okay? They're all the same chemistry. Okay? The polar pi bond acts as an electrophile. I can generate a nucleophile. The interesting thing about that nucleophile that I'm generating is it is coming from the same structure that had a carbonyl, because that alpha hydrogen is acidic. Okay, so lots of things scaffold out of this. That's why we have to look at it and think about it as we go through and approach it. Okay? So let's take a look at these two as practice, because I figured you're not overwhelmed enough yet. Let's go ahead and see what you guys can do with these two. They're really kind of the end of chapter 10. If you got questions, raise your hand. I'll come to you, but these kind of review the stuff that we've just looked at. In all cases, you are going through an enol, and that's one of the things that makes this chemistry tricky, is that we don't see the enol, but it does form under both acidic and basic conditions. Both these reactions are running under acidic conditions. Okay? And the second reaction is a little more obvious because it says H+. Okay? So we protonate the oxygen first. Okay? It doesn't want to be positive. That then sets up the intermediate structures in here through resonance. We can remove that hydrogen, making the enol form. The enol is nucleophilic at the carbon identified, okay, in blue. That cannot be shown as a valid intermediate in our mechanism. Why not? It does not exceed the octet.
There's too much charge.
It's not that there's too much charge, but getting at the right idea. As a hint, it's in blue. Okay, well, I would care. That's what makes it a nucleophile, right? As another hint, it's in black. Kind of fun. It's black and blue. Kind of like your brain, right? What conditions are we running under? Acidic conditions. Can we have a negative carbon? No. Okay. Because of that acidic hydrogen, we cannot show that blue structure. We cannot show a formal negative there. But we can show the repercussions of it existing. The repercussions being that those pi electrons can come out and attack bromine. What's the result? We've now done a substitution. Does oxygen want to be positive? Nope, so it can lose that hydrogen. So far okay? I haven't talked about pyridine. That's also a legitimate second step. Okay, so that is the end result of step 1. Anybody notice some interesting features? There is a chiral center there. So I should, in theory, be showing wedges and dashes. Why can I dodge that bullet? It's actually a couple reasons.
We didn't start.
I can still end with it, sort of. I'm not showing it because I know what happens after step 2. Okay. The other reason, I end up with 2 products. One where the bromine's wedged, the methyl's dashed. Methyl dashed, bromine wedged. I think I said the same thing, but enantiomers. Okay? So we do get 2 products there, and yes, if we were to stop, we'd have to officially draw it. Okay? But we aren't stopping there, we do move on to the next step. So that anytime you see a carbonyl acidic conditions, you should be drawing immediately the enol. Just jump to it. Okay? That sets you up with your nucleophilic carbon. Now you can try and decide where to go from there. Okay? You need to be making that leap fast. Why did I do the substitution the way I did and not to the other side? Weren't there 2 possible places I could have removed that hydrogen from? Purple versus blue? Why did we go purple and not blue?
Purple's going to be more acidic.
Has to do with our product. The pi bond is more substituted. We're expecting the thermodynamic product here. There's nothing to suggest that we would get the kinetic. Acidic conditions are almost always going to favor the thermodynamic product. Okay? We're going through and removing a hydrogen, non-polar carbon-hydrogen bond without using a base at all. Okay? No base. We're looking at a very easily reversible reaction. We're probably going to get the thermodynamic out of this. Okay? So that does end with that product. We then add the pyridine. Okay, I drew pyridine down below. Probably wasn't a very good hint. Should we give another hint? Might help if we added this. What does that mean? Heat. Evaluate pyridine for me. Pyridine is a base. So I have a base and heat. What do I need? I'm probably going to do an elimination. If I only had a leaving group. Oh wait, what did I just attach to the structure? Bromine, which happens to be a good leaving group. What happens? Our pyridine can share electrons. Kick out the bromine. And we end with our final product. That's not a CH3 up there. That is our final answer. Multiple steps. We have to realize how we cascade through each of those and where they end up going. Okay? Why do I not care about the stereo center? Do I have a stereo center anymore? Nope. So I don't need to worry about it. Make sense? As soon as you see carbonyl, you should be thinking enol every time. Okay, so I'm going to erase all that in 3, 2, 1. Top one. I said we could ignore PBr3 for the moment. What do we see in that reaction? I agree, bromine is a great electrophile, which then means what do I need to find in the other species? A nucleophile. A nucleophile would be a source of electrons. The source of electrons could easily be next to a carbonyl. All right? If I just remove that hydrogen, I could go through and do my enol processing. Everybody okay with that? I'm not going to draw out all of those carbons. Okay. Slight problem with that. Is that hydrogen remotely acidic? Said another way, is it the most acidic? Why are you saying no?
Because there's hydrogen attached to an oxygen.
There's a hydrogen connected to an oxygen, which is also connected to a carbonyl, which is carboxylic acid. Okay. So this one is under acidic conditions. We would expect a self-catalysis here, except that we can't pull that hydrogen off. There's more acidic hydrogens present. Okay. At no level do we get a sizable amount of that nucleophile because of the carboxylic acid functional group. So that kind of puts us dead in the water. Okay? But I said you could theoretically still come up with it. So let's just say, for giggles, that it happened. Our electrons come back down. Those come out, attack our bromine. Right? And we would end up with right? And because it's under acidic conditions, I only have to do one substitution. Right? So the complexities with this is that we shouldn't expect that. Okay? Because that oxygen is there, that makes that carbon-hydrogen bond not acidic, the reaction doesn't go, everything kind of dies in the water there. Except, it wasn't just Br2 and water that was added. In fact, if we even think back to this, why did we add water? There's no reason to add water. Okay? What else was in the solution? What does PBr3 do? Replaces the OH with a bromine. Once that has happened, what happened to the acidity of that hydrogen? It's actually become slightly more acidic. We now have the ability to cascade our reaction out. And at the end of step 1, we would end up with this structure. Well, then what does step 2 supply us with? Me and subtle hints. Okay, you can do a step better than telling me what I just circled. Oxygen would be a weak acid. Okay, it could be a weak base. Does anybody see anything acidic? What do we see here? An electrophile. What can the oxygen do? It could be a nucleophile. I wish there was a good leaving group there. We end up with the same product, but we're allowed to run this reaction. The carboxylic acid won't form the enol. Okay? That hydrogen is not acidic enough when we have a carboxylic acid. Okay? So instead I'd have to convert it to PBr3. That makes the hydrogen acidic enough that it can form some of the enol. I now have the active nucleophile that can run the reaction. Okay? So carboxylic acids, no go in enol chemistry. Okay? All the rest, yes. Okay? Okay, even esters are kind of piss poor when it comes to enol chemistry. Okay? So I'm going to advance in 3, 2, 1. You guys want to take an attempt at synthesis? Well, I'm going to take that as a no. Okay. This is where we move into chapter 7. It's all about the addition of our polar pi bond. We've got all the sections kind of listed out here because I was trying to come up with some way to organize how I thought through this. The first couple parts are the general pieces of what a nucleophilic addition is. It's all about a polar pi bond, which means carbonyls. That's why it segues very nicely from chapter 10. Okay? So we're looking at the carbonyl functional group and how it reacts with nucleophiles. Well, what nucleophiles? How about hydride nucleophiles? So hydrogen. How about carbon nucleophiles? Okay? What is special about both our carbon nucleophiles and our hydrogen nucleophiles? How would I draw a hydrogen nucleophile? Tell me what to do. What charge? Okay, so I got a negative charge. Is that a hydrogen nucleophile yet? No. How do I make it a hydrogen nucleophile? Okay, add an H. Okay, thank you. That's all I needed. Good. Okay. What can you tell me about a hydrogen nucleophile? It is very reactive. That is a stupidly strong nucleophile. Okay. How do stupidly strong nucleophiles react with carbonyls? Okay. That's hydrogen. What about carbon? How do I make a carbon nucleophile? Same thing, except with carbon. Good last minute addition. What can you tell me about carbon nucleophiles? They are also stupidly strong nucleophiles. Guess what you're looking at in chapter 17? Stupidly strong nucleophiles. How do they react in a nucleophilic addition? Guess what happens when we move into the next chapter? The not stupidly strong nucleophiles. Okay. Interesting thing that we might have thought was in our stupidly strong nucleophile that isn't. Negatively charged oxygen, wouldn't that be considered stupidly strong? It's negative. We've considered that a strong nucleophile before by definition because it's negative. It is a strong nucleophile. It's not a stupidly strong nucleophile. We need it to be a stupidly strong nucleophile so that we run an irreversible reaction. Oh, crap. Going back to those stupid words again. Yes. Okay, what we're looking at in chapter 17 is irreversible nucleophilic additions. Because what happens when we move into chapter 18 is our nucleophiles can now add reversibly. And by adding reversibly, things can go sideways very quickly. And instead of reacting just with carbonyls, we can look at how they react with conjugated carbonyls. Okay? So it changes the chemistry significantly when we move to just strong nucleophiles. Okay? Which is largely the last section when we see Gilman reagents in conjugate additions. That's how we transition into those just strong nucleophiles. So let's pick the easy ones first. Let's almost pick the easy ones first. Aldehydes and ketones, why they're important? They show up freaking everywhere. Okay? They're largely, or they have a large presence in a lot of sense. They show up in our steroids, progesterone, testosterone, progesterone, that "one" ending because of the ketone functional group that we find within them. Okay. We've got a bunch of flavorings up above. This slide went all sorts of haywire when I switched different adaptions, so whatever. The nomenclature of aldehydes and ketones, what do you guys think? You want to look at it, move into some reactions. Okay, you left it to me. We're moving to reactions. Where's the chemistry in the carbonyl? What do you see as reactive for a carbonyl? Okay. We've got the pi bond. So pi electrons. We have Lone pair electrons. Which might we expect to be more reactive? Probably the pi bond because
P orbitals.
p orbitals. Okay. So if we were to look at a reaction, we might start our arrows there going outwards. If we went through and did that, okay, where would we attach the electrophile or our positively charged atom? Should it go to the oxygen or the carbon? Why are you saying it should go to the oxygen?
Negative.
I don't quite accept that.
Carbon would be partially positive because
Why is the carbon partially positive?
the oxygen.
The oxygen is electronegative. Yeah. The oxygen being electronegative is going to pull those electrons up towards the oxygen, so we'd expect to attach our electrophile up above, leaving the carbon positive. Okay. The reason I'm drawing this is that we also have a resonance structure for that, right? Could have just as easily drawn this. Which of these two resonance structures is more valid? So I've got to vote for the left. Why is the left resonance structure? So the one, make sure we're all agreeing, the one with the carbocation you're saying is best. Yeah? Okay, so we're saying that one is the best. Why is that one the best? So we've got a carbocation in the tertiary position, which would suggest that would be the most stable. Well, did I have any other place that I could put a carbocation? We look at those two answers. Only one of them has a carbocation, so I don't quite accept that as an answer.
Carbon can hold the positive charge better than the oxygen can.
Why are you saying?
Because the oxygen is more electronegative, so it doesn't want to have positive charge.
So we're saying oxygen does not want to hold a positive charge. Okay. I really love those answers. Unfortunately, they're wrong, which was something that in first semester we addressed on multiple occasions, and this is where it comes back to haunt you. Sort of only haunt you. The one on the left is not the best. The one on the right is the best. Why is it better than the one on the left? It's the octet rule. The one on the left, the carbocation, does not have an octet. That, by definition, makes it worse than the one on the right. Even though the balance of electrons makes more sense in the one on the left, it's not the best Lewis structure. Okay, everything is better, according to our Lewis rules, with an octet. Okay? The reason, again, why we're addressing this, because this goes back to how we set up our mechanism. We said the pi, highest energy electrons, should react with the electrophile. If we did that, that would make the structure that we drew first, right? The structure that we drew first was actually a shite structure. What does that mean about our arrow? That wasn't the best arrow to use. What should our arrow actually be? The lone pairs should react with the electrophile to make the structure on the far right first. Does it change anything about the detail of what we understand within the reaction? No. Okay. But that very subtle difference is massive when it comes to the online homework. The lone pairs are going to be the one that react when we're looking at choices between the pi bond and the lone pair electrons. The lone pair are the ones to react first, not the pi. Okay? So, can I erase all that? Or most of that at least? So that means when we go back and look at all of this, it's probably easier just to erase everything and start again. When we look at the reactivity of the lone pair electrons and the pi electrons, it's actually just the lone pair electrons. I don't care about the pi electrons. Okay? So we started with two things being reactive. We now only have one. How else can this structure react? That carbon is partially positive. I have an electrophile. So there's really two sites of reactivity. We have the oxygen lone pairs, and we have the electrophilic carbon. Okay? As far as the carbonyl goes, that's it. Okay? Would I expect that oxygen to share electrons with an electrophile? Or should it share them with a hydrogen?
Probably a hydrogen.
Probably a hydrogen. Believe it or not, it only goes to a hydrogen. It doesn't go with the electrophile. What's the difference between an electrophile and a hydrogen? An electrophile is not hydrogen. It doesn't mean it does not have hydrogen. Hydrogen is very easily accessible on the surface of a structure. Electrophiles are embedded inside. Okay? The oxygen being tied up with its hybridization in the rest of the carbonyl, okay, cannot react with electrophiles because the electrons are too tied up into the carbonyl structure. Okay? Which means we do not see the oxygen act as a nucleophile. We only see it act as a base. So in our carbonyl that had all of these electrons floating around, we're now down to only two things. We have the oxygen that can act as a base, and we have the electrophile of our carbon. Technically, we have one more option, just because we can always be irritating. Every time you see a carbonyl, what should you think? Enol. You have an acidic hydrogen. Okay? That you also need to keep track of and consider in your reaction. Okay? So what we've done is just boiled down every carbonyl functional group, what can possibly happen within them. Now what we want to do is apply it. Okay? Like I said, this mechanism is all about nucleophilic addition. We've looked at the acid reaction already, chapter 10. We looked at the lone pair electrons acting as a base, officially all the way back to acids and bases. Okay? So really the only new chemistry that's happening with our carbonyl has to do with the electrophilic carbon. So I want to now do a nucleophilic, because I need it to react with the electrophile, a nucleophilic, and now addition. Why would it be an addition? If I add a nucleophile to that carbon, what happens? What's that? Yeah, I can neutralize the electrophile. How? So there's a nucleophile sharing its electrons with that carbon. What happened to the carbon? It is less partially positive. Yeah, how? I would argue at this point it is not less partially positive. Well, it is way, way less partially positive. So,
well,
Or it
not only
becomes
that, you're
yours.
allowing electrons to go back to oxygen.
we've exceeded the octet on that carbon. The pi electrons move up to the oxygen, meaning what happened to the pi bond? It's gone. I started with a pi bond and I lose it. What type of reaction does that? Addition. That's why it's a nucleophilic addition. Okay? You're looking at each of the pieces along the way and how they stack and react. Chapter 17 looks at your hydrogen nucleophiles and your carbon nucleophiles. Carbon nucleophiles we have seen in a few cases. Gilman is your enol nucleophile. Wittig and Grignard. And you're like, what the hell? That doesn't sound like carbon. That's because they aren't carbon specifically. Those are the names of the people that discovered them, because are carbon nucleophiles easy to come by? No. So the instant we can find a carbon nucleophile, stamped with a name. That's where we get the Wittig reaction and the Grignard. The acetylide is your carbon. That's your triple bond. We saw that all the way, way, way back in our acid-base kind of sections. Okay? So we'll see that and how that reacts again. Hydride as a nucleophile. Is hydride stable on its own? So H minus. No, we have to stabilize it. Okay, we could do sodium hydride. That supplies hydride. But what did we say sodium hydride acted as? A base. It cannot act as a nucleophile. It turns out the reason sodium hydride cannot act as a nucleophile is because it's massive. Sodium hydride is huge. What was that little head tick, Sam?
Why is it huge?
What? An A and H, man, isn't that huge?
H is pretty small.
H is pretty small, sodium is pretty small. Why is that huge? That bond is so incredibly weak that for it to exist, it must exist in the larger superstructure, like a salt, like table salt, which means it is not soluble in organic solvents. If we throw it into water, it's explosion time, so we have to go into organic solvents. Because it does not dissolve in the organic solvent, the only place sodium hydride reacts is on the surface of the material, which means it's huge. Okay? It is so huge it's actually structural in its reactivity as opposed to like molecular. Okay? So sodium hydride is insanely bad as a nucleophile. It can only act as a base. Okay? So how do I get a negative hydrogen? I don't know, have we seen places to get negative hydrogens before other than sodium hydride? You can cheat, it's on the screen. BH4, sodium borohydride, BH3, both of those reagents gave you negative hydrogens, albeit in slightly different circumstances. So when we're looking at our hydride nucleophiles, whoa, ignore that for a moment, we need to stabilize it. That's where our sodium borohydride comes in, and a new reagent, lithium aluminum hydride. Okay? Both of those supply hydrides as nucleophiles. It's in their name, sodium borohydride, lithium aluminum hydride. Okay? All they're doing is supplying a negative hydrogen. So you can see them and immediately just say it's a negative H, attack, move that up. The result, so I'd have a negative oxygen. How do I stabilize that negative oxygen? Add a hydrogen from our acid, and we'd end up with our final structure of just the alcohol where I've added the hydrogen across. Okay? So hydride nucleophiles. Are those conditions the same? No. Why not? Okay. With that, I'm going to double back. Oops, almost double back to the spider diagram that summarizes all of the reactions that come out of it. I know there's a lot of text up there, but it's at least there. I'll let you stare at that for a little bit. But we're done for today.